Or to the cloud. So perfect, we can start. So amazing. I didn't expect so many people actually today to show up. Yeah, so welcome. I'm Alessio. I'm a postdoc at Boston University with Aldo. And yeah, thanks to him and also to you for this opportunity. And in these 6 lectures, I will try to basically explain what I've been doing during the last few years of research. This is not exactly what I did, but it's like the fundamentals of what I did. So these are, I think, core ideas that anyone working in this field should know. So I will try to go through some of the fundamental ideas and try to basically give you the notions and make you understand the kind of reasoning you do when you try to derive results in this field. But what are we talking about exactly? So as you know, the name of the course is a bit of a random variable. It's called pure exploration or active sequential hypothesis testing. Some other people call it sequential experiment design. But what is it exactly? So let's start. This is a problem. Okay, so the core idea comes, I think, from Chernoff in the 50s. He has this paper called Sequential Design of Experiments. It's from 59, I think, 1959. Chernoff, very famous statistician, PhD of Wald, another great guy. And in this paper, he proposes this problem. So let's say you are a scientist and you want to study some phenomenon. You want to understand what is like the true hypothesis about what's going on, okay? And you design an experiment, you do the experiment, you observe the outcome. Based on the outcome, then you decide what to do next, or maybe to conclude, and you state your conclusion about what's going on. So effectively, this is like a closed loop system, right? So we have some system. You are the scientist, you act on the system through some experiments. In control theory, this is also called action. Also in reinforcement learning, this is also called action. And after you actuate on the system, you are going to observe some output, some outcome. And based on this outcome, you will decide what to do next. So this is you, the scientist. So indeed, we have a closed loop system. And whenever we have this closed loop system, we are talking about active learning in a sense, because you are trying to do, the next thing you will do is based on what you have observed so far, okay? So this is also another reason why it's called the active hypothesis testing, because you're actively deciding what to do next based on what you have observed so far, so you're closing the loop. This has many applications, I think. One of the applications is like in best arm identification. Best arm identification is a problem in multi-arm bandits. So let's imagine you have like K options, like it could be K drugs. You want to test which drug is the most efficient. So you can associate which drug some mean value of success. And then what you want to do is to try to understand which drug is the best one. So your hypothesis is to find the best drug, okay? In reinforcement learning, another example is trying to find what is the best policy. So in reinforcement learning, we are trying to maximize the reward that we collect from some system. So you have some system, you can take actions on this system, and the system will output some observation. This is called state, and reward. And in reinforcement learning, usually the goal is to try to find a sequence of actions that maximizes the total reward that you collect from this system here. So trying to find a policy that maximizes this cumulative reward, it's also a hypothesis testing problem. You want to understand which policy is the best one. And this is also called, so going back to the name of the course, another name is pure exploration. Not to be confused with the exploration-exploitation trade-off that we usually have in reinforcement learning. As you can see here, in reinforcement learning, the objective is to maximize the reward. But in pure exploration, we don't care about maximizing the reward. We want to find the best policy, which doesn't mean that you want to maximize the reward. You can take as many bad actions as you want, as long as you can identify the best policy as quickly as possible. So this is a first difference, not to be confused with exploration, exploitation. And the term pure exploration is the machine learning term. The active sequential hypothesis testing name is the statistician term. Okay, so what I will do today is try first to explain some ideas through an example. So we're gonna go back to the two drugs example. So the drugs example I made before of trying to understand which drug is the best one. And after that, we are gonna formalize the problem. Then we are gonna take a small break. And then we will see if we can manage to derive the first sample complexity lower bound today, okay? So let's look at this example, the two drugs. So we want to test which drug is the most efficient. So the efficacy. So let's denote the drugs by A1, A2. And whenever we give the drug to some user, we are gonna see some response, success or failure. From a statistical perspective, we can model the response as some Bernoulli random variable that we call X, distributed according to some Bernoulli distribution with parameter PA, where A can be A1 or A2, depending on the drug that you chose. So now let's say we are in, you have already tested these two drugs several times. So let's say you have chosen drug one has been chosen, let's say, N1 times with M1 successes. And drug 2 has been chosen N2 times with M2 successes. So now the question is, what should we do next, given that you have observed these outcomes? So we can, for example, define what is the empirical average for drug 1, which is M1 divided by N1, and the same for the second drug. So we have this information. And as a scientist, now you need to decide, okay, what I'm gonna do in the next round, which drug should I choose? How do I understand which drug is the best one? So here it's a hypothesis testing problem, the one that we are trying to solve. We know that there are some true underlying probabilities of the efficacy of each drug that we can indicate by P1, P2. And what we are trying to do is basically we want to test the null hypothesis that P1 is better than P2, or the alternative that P2 is better than P1. So the second drug is better than the first one. So we are trying to do this hypothesis testing problem. Do you have an idea? Anyone? So the idea, a very simple idea, is maybe to try to think of what could be the worst possible scenario. So what could be the worst possible scenario in this case? And based on that, you can try to think, okay, based on this worst case scenario, we want to maximize the evidence that we can collect in the next round based on this worst case scenario. And we are gonna act based on this. So the worst case scenario is the scenario where actually both drugs have the same efficacy, if you think of it, because you cannot really distinguish between them. If the two drugs had very different mean values, then it would be very easy. But when they are the same, there is really not much you can do, right? So this is the idea of trying to construct some alternative model that is confusing to you. Okay, and this will be very, very important in later when we try to derive a lower bound. So a simple idea is to test the hypothesis now in round n that the true value of P is simply equal to our empirical average versus the alternative hypothesis that P is equal to some value P bar that is the same for both arms. So this is our confusing model. Now, finding P bar can be cast as an optimization problem, but a very simple idea is to define P bar to be a convex combination of the empirical average that we have observed. So you can define it as M1 plus M2 divided by N1 plus N2. And this is simply equal to N1 divided by N1 plus N2 per times P hat N1 plus N2 divided by N1 plus N2 P hat N2. This could look like an artificial choice, but we will come back later to this of why mathematically this is the right choice. But the idea is that you're trying to find a model where both arms are the same and such that it's it's confusing in a maximum way. And we will see that this notion of maximum will be from a divergence perspective using the KL divergence. So let's say we are doing this hypothesis testing problem now. We are testing if this the true value of P is exactly equal to the empirical average that we observed so far, or maybe it's equal to this alternative model where both arms have efficacy P bar. The simplest idea now is to try to maximize the evidence in this case. So for example, we could decide to choose the next action so the next drug to test based on the drug that will give you the highest amount of information. So we can characterize the amount of information by using, for example, some measure, or in this case, we use a divergence that we call I. So we're going to measure the divergence between the Bernoulli distribution of parameter P hat NA and the Bernoulli distribution of parameter P bar. So the measure that we're going to use here, it's the KL divergence. And in this case, it's a Bernoulli KL divergence. We are also going to write dxy equal to x log x divided by y plus 1 minus x log 1 minus x 1 minus y. So here I didn't write p hat p bar just for simplicity. So in the following whenever we have Keller divergence with Bernoulli distribution, I'm gonna write small d for simplicity because it will appear many times. Okay, so we choose this measure, this divergence here, to try to quantify the evidence. What it means is that the largest the difference between p hat and p bar, and the more likely you should choose that drug. So now let's say that one of the drugs has not been chosen that much. So let's say we have chosen drug one most of the time. What will happen is that p bar here, so let's say this is p bar n. So what will happen is that if we have chosen only drug one most of the time, then this p bar will be essentially very similar to p hat n1. So if p bar is very similar to p hat n1, then drug one will have a very small divergence. So there is not much information we can gain from that drug. So what will happen is that we are going to choose drug two. So as you can see, this is sort of a stable way of choosing drugs. And you can show that asymptotically. What will happen is that you will sample an infinite number of times both drugs. So N1 tends to infinity, so also N2 tends to infinity. And what will happen is that your empirical average will converge to the true average. But what happens to P bar N? So P bar N is this convex combination of the two efficacies. What will happen is that this P bar N will converge to lambda P1 plus 1 minus lambda P2 for some convex combination lambda in 0, 1. So the meaning of lambda, if you remember, P bar is defined in this way. So this is exactly the quantity lambda at time n. We can define it in this way. And it represents the proportion of times we have sampled arm1, the first drug. So asymptotically, this lambda represents the static sampling ratio of drug one, and 1 minus lambda represents the sampling ratio of drug two. And you can also show that the value of lambda that satisfies this equation will be the optimal sampling strategy. And this quantity is also called Chernoff information. I hope it's clear so far that asymptotically this P bar will converge to some convex combination where there is this factor lambda representing the sampling ratio, and the value of lambda that achieves this equation here, there is just one value of lambda, will be the optimal sampling strategy. And the value of lambda achieving this point here, this equation, gives you this quantity here that it's called the Chernoff information. So this is the amount of evidence at the optimal point. So if everything's clear so far, we can start by introducing a little bit the technical part of the problem. So no question regarding this, everything's clear. Yeah. Okay, so here we're gonna give some definitions. I'm not sure about the background of most of you, so I'm gonna use stuff from measure theory, probability theory. So please stop me in case something is a bit too much, okay? Yeah, so we defined a probability space to be this triplet. This is the sample space. Yeah. Yeah, I think it's a bit slow. Yeah, the sample space is too much. Let's see. For those online, we have some problems with the screen. Just 1 second. Okay, I think we are back. Yeah. All right, so we have the sample space. We have the sigma algebra. And then we have some probability measure. I don't really have the time now to explain all of this, but what is important here, it's the probability measure. Which defines basically the way we can compute probabilities over this space here. We also define random variables to be mappings from this sample space to the reals. And when we use the sigma algebra, I always refer to the Borel sigma algebra, which is like the smallest sigma algebra generated by the open sets. That we denote in this way. Another concept that we're going to use is also the notion of filtered space. Which is a probability space where we define also filtration. So we have the sample space, our original sigma algebra, but then we also have this collection of sigma algebra and our original measure. And this is the filtration. And you can think of the filtration as a sequence of sigma algebra. And this sequence here satisfies this condition here. And from a practical perspective, the ft represents the amount of knowledge you have at time t. So if we go back to our example of the scientist that designs experiments, collects outcomes, at time t, around t, the amount of evidence you have collected is basically represented by ft. So ft represents all the knowledge you have up to time t about what happened. Okay, so if we think of this example here, basically we have some outcomes that we're gonna call we're gonna define some space X. And we can think of it as some subset of the reals. We can think of it as a compact set. And then we have the actions that the scientists can take on the system. So I'm not gonna call them experiments, I'm gonna call them those actions, or in the bandit case, arms. So A can be a subset of the reals, it can be a finite set. In the bandit case, it's a finite set because we have a finite number of arms. In the rest of the course, we're gonna assume it to be finite. And then we have the data generation mechanism. So whenever you take an action on the system, you're going to observe some outcome. There is a distribution of outcomes based on what actions you took. It may be also depending on the action that you have taken so far. We are going to parameterize this distribution for simplicity using some parameter space theta. And some parameter theta in this space parameterizes the distribution of x times q, sampled from some distribution that is indeed parameterized by theta, and that it's conditioned on what happened in the past. So it depends on what actions we took at the first time step, on the first observation, second action, and so on, up to xt minus 1 and the action that we took now. So this is very, very general. In the bandit case, obviously, it will be much simpler. If you're familiar with bandits, there is no conditioning on all the past history if the problem is stationary. But in the full generality, you need to consider also what happened in the past, right? This xt, always, if we go back to the drug example, it's a Bernoulli random variable, so p theta will be a Bernoulli distribution. It doesn't depend on the entire history, but just on the action that you took. So I hope this part is clear. We still need a couple more definitions. We are also going to define what is a strategy. So we define a strategy pi to be a collection of policies such that pi t maps from histories to actions, and it can be a distribution over actions too. So this ht is defined, so ht minus 1 is defined as this sequence here. So the action that we take at time t, it's sampled from this policy pi t. So at is going to be sampled from pi t that is conditioned on the history that we have observed so far. So this pi t is the sampling rule. It decides what to do next based on what we have observed so far. So the rule that we defined before to choose the action that maximizes the evidence can be seen as a deterministic policy. It's not a stochastic one. But in full generality, the sampling rule can be stochastic. It doesn't need to be deterministic. And the last ingredient is to define also a way to make an inference about what is the true hypothesis. So we define some hypothesis space D. We can also call it decision space. And we will make the assumption that there exists some mapping that maps from parameters to this hypothesis space, so that the true hypothesis for a given parameter is d theta. So if we think of the drug example, theta, it's basically the mean values of the efficacy of the drugs. And you can define d theta to be simply the argmax between the two values of p. So we will make the assumption also that this d theta is unique. So for each parameter theta, d theta is unique. Yeah, clear so far? Okay, so now that we have basically all the ingredients in place, there are two main objectives in pure exploration. Yeah, the FT. You mean this or? Yeah. Yeah. So FT, it's formally defined as the sigma algebra of all the data you have observed so far. That's basically the definition. It represents all the knowledge you have up to time t. So if you say that a random variable is measurable with respect to ft, it means that given all the data you have up to time t, then you can compute that random variable. It's deterministic to you. Okay. So another concept we are gonna use is the concept of stopping time. Or stopping rule. So here, stopping time, it's basically a function tau that maps from the sample space to the natural. And the property of tau is that the event tau equal to t is measurable with respect to ft. This only means that the event, if you should stop or not, you can always compute it. Okay, nothing fancy. You just need to define it in a way that it's computable given all the data you have at time t. It doesn't need to depend on the future or on weird stuff. Okay, so there are two main objectives in pure exploration. There is the fixed budget objective, and there is the fixed confidence objective. In the fixed budget, I give you a number of rounds, fixed. Let's say I give you capital N rounds. And I want you to find with the highest accuracy what's going to be the true hypothesis, given this maximum number of rounds. In the fixed confidence, instead, what I want you to do is to try to quickly find the true hypothesis. So you need to be as quick as possible, but at the same time, I also want you to be confident about your inference. So in the fixed budget, Yeah. First, I forgot a very important thing. We haven't talked about the inference rule. So we also need this last ingredient, which are the inference rules, because we didn't define it. Yes. So it's a collection of mappings where each IT maps from histories to decisions. So basically, this is your mapping that, given all the data, outputs what should be the true hypothesis. And we are also gonna denote by the hat t the inference that we make at time t. Okay. So in the fixed budget, yeah. There's implementation software in the world, or was this like the ICP? This is part of ICP. Yeah, this is my generalization of this problem. Yeah, because originally all the stuff was defined for best term identification, but then I try to make it more abstract. So usually, if you look at best term identification papers or this stuff, you don't see this. It's a specific problem of what I'm describing now. So in the main part of the course, we're going to look at bandit problems, but in the last lecture, we're going to go back to this and see how this can be solved optimally. So, okay, in the fixed budget, what are we trying to do? We are trying to maximize the probability that we are making the right inference at the last round, in the last round. So we are given a budget of n rounds. And what we want to do is to maximize the probability that our inference in round n will be equal to the true hypothesis. Now, this probability, I'm gonna write it in this way to indicate that it depends on the sampling rule that you choose. It depends on the problem theta, on the parameter theta. And the real issue here is that we need to find pi and I such that we can maximize this probability here. So this is infinite dimensional problem because pi, if you remember, is this collection of policies. Policies are distributions. Also, I, it's a collection of inference rules. Each inference rule is a mapping, so it's a function. We are looking over a space of functions. So this is a quite complex problem, but we are gonna try to see if we can solve it at the end of the course. The other problem is the fixed confidence problem. So in the fixed confidence, we are trying to minimize the sample complexity, which means we are trying to minimize the number of samples we need to make an inference with some degree of precision. So we are going to introduce a parameter delta that tries to measure the error. And 1 minus delta will be our confidence. We also need a way to decide when to stop the sampling process. And this is defined by a stopping time. So we also need tau, a stopping time, that tells you when to stop. Okay, so we are trying to minimize the number of samples, which means that we are trying to minimize this value of tau. We are going to look in expectation at the value of the stopping time. But at the same time, we also want to guarantee a confidence of at least 1 minus delta that our inference is correct. So we are going to minimize the sample complexity subject to this constraint on the correctness. And what's interesting here is that we are maximizing not only over pi and I, but we also need to maximize over stopping rules. So it's not only a problem of deciding the sampling rule and the inference rule, but we also are looking for what is the best stopping rule. So this problem is slightly more complex than the fixed budget, even though in literature, you can find more results on this. And we are gonna cover this problem for most of the course. Yeah. Sorry? Right. Yeah, we want to minimize. Thank you. Yeah, there was another question. Yeah, thanks. Yeah. So I hope it's clear so far. So if it's clear, we can take a small break, maybe 5-10 minutes, and then we go in trying to derive the first lower bound. Okay, so now for the rest of this lecture and probably also a bit of the next one, we're going to look at the lower bounds. So what we are going to do is try to understand this fixed confidence problem in a very simple setting called the bandit setting. And what we are going to do is try to understand what is the infimum value that can be attained. So what is the best an algorithm can do in multi-arm bandit problems? What is the minimal number of samples that we need on average? So just to define what is a multi-arm bandit problem and what is the best arm identification problem. So I think, sorry, just 1 second, okay. So multi-arm bandit problems is a problem where there are k arms. And whenever you select an arm or action, I'm gonna use this term in the same way. Whenever you select an arm, you're gonna observe an outcome that is sampled from a distribution, p theta, the one from before, but we don't have the condition on the entire history. It depends only on the action that you chose. And what it's important to us, it's understanding which action A has the largest average outcome. So for a parameter theta, we define mu A theta to be the expected value of X sampled from this distribution, and it's the expected value of X. And in integral form, we are gonna write in this way here. So it's gonna be integral of X, P theta dx given A. And what we care about is understanding which arm has the largest mean value. And we are gonna define this by, we're gonna denote this arm by A star theta. So if you think of it, this argmax A mu A theta is exactly the D function from before. And and we are going to assume that the problems that we consider have only one unique optimal arm. Is that a sensible assumption to just assume one unique optimal arm? Well, it depends, but if you have like some uniform prior over the space of parameters, you can show that with probability 0, you will pick a model with multiple optimal arms. So if you don't have any knowledge about the problem, then it's probably a good choice to assume that there is just one optimal arm if you are gonna uniformly sample from the space of models. Okay, so we're gonna work with this model for the rest of these lectures, except when we're gonna move on to MDPs. And we're gonna look at the fixed confidence problem. And in the fixed confidence, we need a couple of definitions. The first definition that we need is the definition of what is a delta probably correct algorithm. So we define an algorithm and an algorithm in our case is simply the combination of sampling rule, inference rule, and stopping time to be delta probably correct if the probability that we are gonna estimate the true hypothesis is at least 1 minus delta. So the probability that we are gonna make a correct decision time tau. So here I'm gonna omit the notation here. So I'm gonna omit the superscript pi here in the rest of the lecture, but it's there. So this probability depends on the sample rule. I'm just gonna leave the theta because we will change it from time to time when we deal with different models. But you should always remember that this probability is with respect to the algorithm that you are using. So with respect to the sampling rule, the inference rule, the stopping rule, okay, that you are using. And now, since we are dealing with arms with this simpler model than the general problems that we have defined before, I'm gonna write a hat tau here instead of D because our decision is an arm. So so this is our estimated optimal arm. So just to make the notation a tad simpler. And another important thing is that we also require our algorithm to guarantee a finite expected sample complexity. We don't want this to explode. And this also implies that the probability that tau is finite is equal to 1. But observe that the reverse is not true. So guaranteeing that tau is finite doesn't mean that the expected sample complexity is necessarily finite. Yeah, this is a homework question maybe. You can think of like the sum. So for a sum to converge, it's a necessary condition that the limit of the elements tends to a finite value. But this is just a necessary condition. Doesn't mean that the sum will converge. Okay, this is exactly the same because this expectation is like a sum. And this probability, you can think of it like a limit. So this converging to something doesn't mean that the sum will be finite, but the sum that is finite implies that the limit converges. So you can try to prove it on your own. This. Okay, so this is the most important definition so far. The second definition that we will use is definition of alternative model. Yeah.
Is this delta type holds for every theta using the type of theta, or is just for this theta?
Right. Thank you. Yes, it holds for all the theta in the parameter space. So we define algorithm to be delta PC if this condition holds uniformly on theta. So for each theta, we need to guarantee this confidence. Okay. And yeah, thank you for the observation. Okay, but before I give you this other definition, let's think again about the drugs example I made before. So in the example, I told you about the idea of trying to derive a confusing model. The idea is basically that you have gathered data so far. So you have gathered a bunch of data. Now the question is, based on this data you have observed so far, what is another model that could have generated the same data with high likelihood? And possibly we are looking at models that have a different best arm. So imagine the case that you have collected data from these multi-arm bandit problems with a best arm, maybe it's one, maybe the first arm is the optimal one. But maybe there is another model with a different optimal arm that could have generated the same data. So if there exists such a model, we call it a confusing model. It's confusing because it has a high likelihood of having generated the same data. Okay. So a confusing model lambda that belongs, it's a parameter. Is confusing if the likelihood of HCT is high under lambda. This is a very, very informal definition. So the right way to do this is through the log likelihood ratio. So we need a way to try to quantify the amount of evidence we collect from a system. And we are going to use the log likelihood ratio to do this. And the idea is that we want to compute the log likelihood ratio between the true model theta and this confusing model lambda, this alternative model lambda, we also say. And then what we will do is try to optimize this log likelihood ratio so that we minimize it with respect to all possible alternative models. So this log likelihood ratio it's, I will define now what is this. It will be basically sum over time of the logarithm of the ratio of some densities. Now we'll define it properly. Now it's just to explain the idea. It will be this expected log likelihood ratio of these densities. This quantifies the amount of evidence. And what we will do in the lower bound is trying to find what is the most confusing model. So the one that minimizes the log likelihood ratio, such that lambda has a different optimal arm. So this will be the main idea behind the lower bound. We quantify the evidence through the log likelihood ratio between theta and an alternative model lambda. And then we try to find what is the worst case scenario. So try to minimize with respect to all possible models that have a different optimal arm. So why we need to find a model with a different optimal arm and not the same arm? Because we want to test which arm is the optimal one. So we need to compare with models that have a different arm, because we are always testing between a null hypothesis and an alternative hypothesis. So the null hypothesis that the arm is this one or another one. Okay. So this also gives us another definition, the definition of an alternative set of models. That we are gonna call it alt theta, all the parameters lambda, such that the best arm in lambda is different from the best arm in theta. Okay, so the first step is write what is this log likelihood ratio. So the log likelihood ratio of the data we have observed up to time t is also defined as the Radon-Nikodym derivative between this measure under theta and this other measure under lambda of the data we have observed so far. Now, maybe some of you don't know what is the Radon-Nikodym derivative. So the idea is quite simple. So let's say you have some two probability measures, P and Q, and you have this event that belongs to the sigma algebra, F. So if P is absolutely continuous with respect to Q, then we have that there exists a function F such that the probability of E is also equal to the integral of F omega Q d omega. What this means is that there exists the derivative of the P with respect to the Q, and this is equal to F. In very simple words, this comes from the idea of monotonic functions. If you think of cumulative distribution functions are monotone. They go from 0 to 1. And what's interesting of monotonic functions is that the derivative of monotonic function exists almost everywhere. So if you have a cumulative distribution function, it's monotone, you can always define a derivative. The derivative is going to be the density, and it's defined almost anywhere. And this definition has been extended more in general for a probability measure. And this is the generalization here. And it requires only absolute continuity. And this condition of absolute continuity simply implies that if P evaluated on this event is bigger than 0, then also Q must be positive. So I think in the last centuries, a lot of mathematicians have been trying, like, or maybe in 1800 or early 1900, some mathematicians were trying to understand what is a generalization of this idea that monotonic functions have derivative defined almost everywhere. And this generalization brought to the definition of absolute continuity. So whenever you have an absolutely continuous function with respect to an absolute continuous measure with respect to another measure, then you are guaranteed that there exists a derivative. So this is very important. Yeah, so as you can see, there is a clear connection. Basically, we are trying to find what is the density here. So the log likelihood ratio is going to be simply the density of the data you have observed so far. So to find the density, we need to define, we can, for example, try to write down what is this given a trajectory. I'm not going to write using integrals, but this notation here, I'm going to use this notation here. So I'm going to use differentials and not integrals. So we need to basically evaluate the this thing here. Why this? Because this is basically the trajectory up to time t. If you remember, each x is sampled from p theta given a. So we are going to have p theta of xt given at. So here we have the dxt times the probability of choosing at. And here it's given the entire history up to time -1. Then times the probability of the xt -1 given at -1, and so on, up to the first time step where there is no conditioning in the pulse. So when we evaluate this Radon-Nikodym derivative here, we are using always the same algorithm. The algorithm is not changing. What changes is the parameter. So when we are going to divide this quantity, but by the same quantity, but under lambda, all this factor pi will cancel out. So when we are going to do this ratio here of all this stuff, basically we are left with this p theta dxt given at, p theta the xt -1 given at -1, and so on, divided by the same quantities but under lambda. Now, if you there is another step before we are good. So in this course, we're gonna make the assumption that the observations are Gaussians most of the time. So the x is Gaussianly distributed. So this p theta is the distribution of a Gaussian, which is absolutely continuous with respect to a Lebesgue measure, which means basically it's absolutely continuous with respect to a uniform distribution. So this theta is the parameter of a Gaussian, the same lambda. They parameterize the average value of these Gaussians. So what we have is that p theta dx is simply the density of a Gaussian times the lambda, which represents the Lebesgue measure. And we have the same also under lambda. We have the density of a Gaussian parameterized by lambda A times the differential of the Lebesgue measure. But then when we replace this quantity here inside the ratio, the lambda will cancel out. And so we are left only with the densities at the end. So we have just shown that this log of the Radon-Nikodym derivative will simply be the sum from n up to time t of the indicator function that we have chosen arm A. We have also a sum over action here of log of the density in theta A of xn divided by the density in lambda A of xn. Yeah. I see some faces a bit uncertain about this. So is there any question or? Yeah. Yeah, so we are using the log likelihood ratio because it will allow us to derive the bound. But the idea is that the log likelihood ratio, if you think from a practical perspective, is trying to quantify the amount of evidence of theta with respect to lambda. So if the trajectory was generated under theta and lambda is a completely different model, what you should expect is that the numerator will be very large and the denominator will be very small. So large divided by small will be very big, which means that you have a lot of evidence that theta should be correct compared to lambda. But when the likelihood, so when the density are similars, what you will get is that here it will be approximately 1 and logarithm of 1 will be 0. So you have 0 evidence of what actually is the system that generated the data. So in a log likelihood ratio, you are always comparing one parameter against another fixed parameter, okay? And you want to see which one best fits the data, simply. So it's a measure of evidence. We could have used also other stuff, but this is a convenient way because it will allow us also to derive a lower bound. Okay, but I mean, I just showed you the kind of formal way to derive it through the Radon-Nikodym derivative, but probably most of you already know how to derive it through densities and so on. Yeah. Yeah, for now we fix the lambda. Yeah. For now it's lambda fixed. We are going to optimize later over the set of lambdas. Yeah. Okay, but even if all the part before maybe it's not clear, I hope this expression still makes sense to you. And we are going to call this the log likelihood ratio at time t. Yes, I will not specify that it depends on theta and lambda, but keep it in the back of your mind. Yeah, so what's interesting here is that when we take expectation with respect to the true model of the log likelihood ratio, so expectation with respect to theta means that all the data is generated by theta. So we should expect the log likelihood to be larger, right? If lambda is different from theta. So what is this expected value? You can show that this expected value can be decomposed in this way. Now we're gonna show why. So this expected value of NAT, we have that NAT, it's simply the sum from 1 to t of the indicator function that you have selected arm A in round n. Yeah, here there is a typo. A_n equal A. And we define this KL here as the expected value under theta of log f theta A of x divided by f lambda A of x. So for an IID sample from theta A, we evaluate this ratio of density, take the log, then we average over all, we integrate over samples here, and this is our KL divergence between theta A and lambda A. So to show this, the idea is simply to use the Watt's lemma. This simply states that if you have a sequence of random variables, IID from some distribution Q, with expected value of xi finite. And you also have a stopping time such that the expected value of tau is finite, then the expectation of the sum or from n equal to 1 to tau of xn is going to be equal to expectation of x times expectation of tau. Yeah, so the idea is simply to apply this lemma to our expectation, to our expression of LT. So remember, it was something like this. So this can also be rewritten in a different way. For example, the idea is to consider a sequence of IID random variables that are basically copies of the of these outcomes X. So these are sampled in the same way under theta. So when we consider these copies, we can also rewrite this expression in this way here. We have sum over A, sum from s equal to 1 to NAT. So NAT is the number of times we have chosen action A up to time t. It was defined here. Of the logarithm of f theta A y s A divided by f lambda A y s A. So these YSA are simply successive observation from the same arm, okay? Because here it is xt, it's not necessarily from arm A, so that's why we need this indicator function. But then through this rewriting, where we denote by the sequence the consecutive observation from the same arm, we can simplify the expression, and we have sum from s equal to 1 up to the number of times we have selected A of this quantity here. And then we evaluate at the stopping time, tau. So before it was for a fixed t, And when we evaluate the stopping time, we also use the fact that we assume expected value of tau to be finite. We can also bring out the sum of reactions from the expectation, and then we are left with expectation over theta of NA tau. And then the expected value of this log, which is simply the Kerr divergence between theta A and lambda A. And this is also called, this entire derivation, the chain rule. Yeah. Yeah, clear so far. Now, what's interesting here is that you can divide by the expected value of tau. So if we denote by WA the expected value of the number of times we have selected arm A up to time tau divided by expected value of tau, then what we have is expected value of tau times this quantity here. And now if I tell you that we can show a lower bound on this, then at this point, you could divide both end side by this quantity here, and you would derive a lower bound on the sample complexity. Okay, but I mean, WA still depends on tau. So what are we really doing here? The idea is that we are gonna optimize with respect to W. Optimizing with respect to W means that we are optimizing the sampling rule, because the sampling rule dictates how we choose actions. WA represents the sampling ratio, so the sampling proportion of arm A. So the number of times we should select arm A on average. So we are going to optimize over this W. At the same time, we still have the problem of optimizing with respect to lambda. Because remember, here we're comparing with a fixed lambda. If lambda is equal to theta, well, there is nothing to optimize. But we're going to choose lambda to belong to the set of alternative models, so it cannot be equal to theta because it needs to have a different optimal arm. Okay, but the first thing is to try to derive what is this lower bound. And this is also called the information processing inequality. And to derive this inequality, we use a change of measure technique, which is based on the Radon-Nikodym derivative. So recall that for two distributions, PQ, where P is absolutely continuous with respect to Q, we have that to exist F such that the P or the Q is equal to F. Okay. Okay, so what we are gonna derive exactly is this statement here. We are gonna show that the expected value of LT for any T is lower bounded by the Bernoulli-Kerr divergence of the probability measure under theta of any event E that is FT measurable. So this inequality holds for any E that belongs to our sigma algebra FT. Okay, so we're gonna show this now. If you don't remember what is FT here, it means anything that can be measured, determined using the data you have up to time t, okay? Not something in the future, but something that you have now. Yeah, so the idea is to use this radon nicotine derivative on this event. So we have shown that, so from before we have shown that LT is also equal to this quantity, right? So now I'm gonna use theta and lambda here. So this also implies that P lambda evaluated at this event is also equal to x minus LT of the p theta. Here we have the integral. And this is also equal to basically expected value of exp minus LT, indicator function of E. So let me repeat it in case it's not clear. So we know that the log likelihood ratio time t is equal to the logarithm of the radon nicotine derivative. For any event E that is FT measurable, informally, you can think of it in this way. Well, what's going on? But formally, what's happening is that P lambda E is equal to the integral over this event E of the expected value of minus LT dp theta. And this dp theta, it's basically integrating over all the possible histories that belong to E. So all the possible history up to time t that somehow are included in E, okay, in the event E. And this integral here over the p theta is just expectation with respect to p theta that we indicate in this way of the expected value of the minus log likelihood ratio. And then we have the indicator function of E because this integral is not over the entire space, but only with respect to E. Okay, so we have this. The first step is to apply the Tower rule. So the Tower rule tells you that expectation of xy, it's also equal to expectation over y, expectation over x of x given y. So we can apply the same idea here. We get expected value, another expected value of x minus LT times indicator function of E given the indicator function of E. Well, this might look silly, but so we can bring out the indicator function because here it's this is measurable, obviously.
Yeah.
Where?
X. There should be the X slash in text. In that.
No, I write it in this way. So, where?
Right, the same. The X.
This one?
Yeah.
So this expected value is over the joint.
Y. Explain Y. That is yes. Y on that. Basically, like one side has X times Y, or side is just X.
Yeah, sorry. Yeah, there is Y. Yeah, sorry. Yeah. So we need to, okay, so what we're gonna do here, the idea is to find a lower bound, okay, for this quantity here. We want to find a lower bound that depends on P theta E. So somehow we need to extract this indicator function. So we need this expected value of the indicator function over E, because that's exactly equal to this quantity. But we need to get rid of this inner expectation. So an idea is to apply, for example, Jensen inequality. Jensen inequality tells you that for a convex function, you have this lower bound. So we can try to apply this to the exponential, which is a convex function. And now the important thing to realize is that this quantity, specifically this one, is actually a constant. And this is a bit tricky to see. So we need to pay attention to what is this thing exactly. And also note that this is also equal to this. It doesn't change the expression if we add an indicator function of E here. So why is this important and how do we rewrite this? So we need to ask ourselves what is this expectation here. So if you have, if you took a course in probability, probably you know that this is also equal to the expected value of LT given the sigma algebra of the indicator function in E. Now, what is the sigma algebra of the indicator function in E? Let's see if someone has an idea. So yeah, we need to recall basically this definition here. So the sigma algebra of a random variable, it's the set given by so the sigma algebra of a random variable x is given by the inverse of x evaluated on the sigma algebra of the Borel sigma algebra. Okay, so this is for a general random variable. In our case, we have the indicator function of E. So what's this? So we have indicator of E inverse for any event that belongs to the sigma algebra of 0, 1. We can also think of all the possible real sets. It doesn't matter too much. So what's this? It's gonna be an empty set if B doesn't intersect with 0, 1. It's gonna be equal to E if B intersects with 1. Here's B. It's gonna be equal to the complement of E, and I use the bar to indicate the complement. If B intersects with 0, and otherwise we have omega. So maybe just take a moment to realize why is that. So it follows directly from this definition, right? Even if we don't use the sigma algebra of 0, 1, but we use this sigma algebra of the all open sets. Then if the intersection, for example, is equal to 1, it means that the indicator is 1, which means that we are on the event E. If the intersection is 0, it means that the indicator is 0. So we are not on E, but we are on the complement. Okay? So now, a random variable that belongs to this sigma algebra can also be written as some constant times the indicator function over E plus another constant of the indicator function over the complement. So any random variable can be decomposed in this way with respect to the sigma algebra. Usually the sigma algebra is like an uncountable number of things, so you cannot really write it in this nice way. But in our case, we have this simple decomposition that it can only be E or a complement. And A can only be constant on E because the sigma algebra is not, it's just too raw, it's too coarse. It's not fine. It's not a fine sigma algebra. It just contains these elements. You cannot like go more into the details. Okay, so we add this quantity here. Remember. So from this expression, we understand that this can also be written as the expectation of LT given E. And this is true because here we have this expectation, this indicator function of E, which means that expected value, the indicator of E is equal to expected value of LT given E on E. So I hope this is at least clear in some sense. But the idea is that the sigma algebra of an indicator is not the same as the sigma algebra. It's not that we cannot just replace with E here, because any random variable that is measurable with respect to the sigma algebra can be decomposed in this way. A and B are constants. A is the expected value of X on E, and B is the expected value of X on the complement. But since here we are multiplying this expected value by the indicator, it means that we are in this case. So we can replace the expected value of LT given the indicator with the expected value of LT given E. Okay, so we were here. So that's the reason why I made this indicator function appear. It didn't change the expression, but now we can use all this reasoning to basically say that what we had before, it's equal to this. And I just said that basically this A is a constant. So we have that this quantity is a constant on E. Since here we have indicator function with respect to E, then we can simply separate this quantity from the expectation. So we obtain probability of E times expectation, exponential minus expectation LT given E. And here we had P lambda E bigger than or equal to this quantity. And so we have just shown that the expected value of LT given E is bigger than or equal to log theta E divided by P lambda E. This also holds for the complement. And we are basically one step away because now we can do the tower rule on the log likelihood ratio. This is simply LT, expected value of LT given E times probability, or with respect to theta here, plus expected value of LT given the complement times the probability of the complement. And so now we can replace these two expected values with these lower bounds. And what we obtain is exactly the Bernoulli-Kerr divergence from before. So this is exactly the definition of Bernoulli-Kerr divergence with these two quantities here. So this completes the proof, and we can use this now to derive the lower bound. So we had that the expected value of L tau, it's also equal to sum over A, expected value of NA at the stopping time, times the KL theta A lambda A. So we know that this expected log likelihood is lower bounded by this quantity. Where E is F tau measurable. So we need to choose the event here. And we are gonna use the definition of delta pack of what is an algorithm that is delta probably correct. So if you remember, an algorithm is delta probably correct is if the probability of not estimating the right optimal action is upper bounded by delta, or the probability of estimating the right action is lower bounded by 1 minus delta. So the idea is to use this event here. This is also called the delta PC event. And this is also the event that appears in the definition of confusing set of models, the alternative set of models. So this is all connected. The definition of delta probably correct algorithm is in the end the most important thing when you define a hypothesis testing problem, because it will affect how you define the set of alternative models and also will define what event you should use now in this lower bound. So we are going to use this event that our guess it's not equal to the optimal arm in theta. Since we are using a delta PC algorithm, under p theta, this is upper bounded by delta. Okay. Very good. We need to understand what is p lambda e. So this is also equal to probability under a parameter lambda that our estimated optimal arm is different from a star theta. So this event here if you think of it, it also contains the event that at a tau, it's equal to the optimal arm in lambda. Because we have assumed that a star theta is different from a star lambda. So we have chosen lambda to belong to the set of alternative models. And because of that, we know that the optimal arm in lambda is different from the optimal arm in theta. So the event where our guess is not equal to a star theta is a bigger event than the case where our guess is exactly equal to this one. But we know by definition of delta probability correct algorithm that this event has probability at least 1 minus delta. And therefore, since this quantity here is smaller than the probability of E, we have just found that the probability of E under lambda must be at least 1 minus delta. Okay. How do we use that? So we add the Kerr divergence between the event E in theta and the event E in lambda. But we know that this is upper bounded by delta. This is lower bounded by 1 minus delta. So let's say these are the true values. This is p theta and this is p lambda. So these are the true probabilities. If we upper bound p theta by delta, maybe this is the value of delta, and maybe this is the value 1 minus delta. This distance here is smaller than this distance here. So the Bernoulli-Kerr divergence between these two values, which are closer, is going to be smaller compared to the distance, the Bernoulli-Kerr divergence between these two parameters. As long as delta is smaller than 1/2. So in the definition, we assume that delta was in 0, 1, but here we're going to make it stronger and assume that it's smaller than 1/2, so that 1 minus delta can be at most 1/2, and the same for delta. So they can be at most in the middle. And so we have just shown that the expected log likelihood ratio of the stopping time is bigger than delta log delta divided by 1 minus delta plus 1 minus delta log 1 minus delta divided by delta. And if we do the trick now of defining WA to be equal to the expected number of times we have selected arm A up to time tau divided by the expected sample complexity, we are left with this expression. On the left, we have the expected log likelihood ratio. On the right, we have the Bernoulli-Kerr divergence between delta and 1 minus delta. So now it's where we do the optimization. The first idea is to optimize with respect to the confusing models. So we take an infimum over possible alternative models, lambda on the left, because we are trying to minimize the evidence. We are trying to minimize the log likelihood ratio. So we make an infimum over lambda that belongs to the alternative set. And there is no lambda on the right. So this lower bound holds for any lambda, as long as lambda belongs to the alternative set. And with respect to the most confusing model, lambda, we are going to play the best optimal strategy. So we are going to do an optimization over W. What is W? W is the sampling rate of each arm. So it's a probability. So for each arm, we have a probability of sampling that arm. And we are going to write that we optimize with respect to W that belongs to the set of distributions over the set of arms. And we are going to write it in this way, where W is this collection of WAs. And we also have expected value of tau here. So this quantity, it's the inverse of the characteristic time. It's also the average amount of evidence you can get from the system. And it's usually called T star theta inverse. So that at the end, we obtain that expected value of tau under theta is bigger than T star theta, Kerr divergence, Bernoulli Kerr divergence between delta 1 minus delta. Yeah, so that's the lower bound derivation. Maybe, yeah, we are 1 minute late, but if there is any question, happy to answer. And then we are going to continue on Monday. All clear? Yeah. Crystal clear. Okay, but on Monday, maybe we're gonna go through again the main steps. I'm not gonna write, but I'm gonna go through again the main steps so that the ideas are clear. And then what we're gonna do is try to study the properties of this problem. We have an optimization problem. How can we solve it? What are the properties of the optimal solution? How can we compute the optimal expression strategies, this W? So try to think about what we discussed today over the weekend. Probably it was a lot of stuff. And then we're gonna meet each other on Monday. Thanks.